I want to back up and take a look at, starting on page 165, how they go through the strain involved in a cyclopropane and a cyclobutane and a cyclopentane, all the way up to a cyclohexane. I wanted to show that to you anyway, it just didn't work out. So here, if I have a pentane, and I got to use the longer bonds to do this, you can see how there's a lot of strain. Those are bent. This is why I can't use the short ones. And what they're showing you here in this diagram, now this is a CH2, but this one is not. But these, for your angle, line up. So there's going to be some repulsion between these hydrogen and these hydrogen. These would be closer together in real life too. And it's going to want to try to twist to get those far away from each other, but it can't. So there's a lot of what's called strain built up in here. And if I put in another carbon, it's a little better. Ooh, that there. So now we're to a cyclobutane. Okay, so what they're showing there, well, they don't show it on this one. They tell you about it, but they don't show you. I'll try to show you. These hydrogen are still lined up, and they're still trying to repel. And that's same true on all the angles, all the viewpoints of looking at it. And so what they're saying is well, those will twist a little bit to make that look like so. So there's a little bit of torsional strain that's introduced there, and that changes these angles. One of them they have listed as 88 degrees. It'd be this one and this one. So the other ones must be 92. But that's because these hydrogen are trying to, if you're looking at it this way, get away from each other a little bit. Okay, then it goes up by a carbon to 5, and this has very little strain compared to the others. I could easily make this using the short ones. In fact, I need to really do that because that'd be a little closer representation than what we have here. Not very much strain on this one. When you get to 6, I forgot that made up for the next thing. When you get to 6, then we're not in a plane anymore because they have to get a, you try to put them in a plane and they don't want to go. And we talked about that. So here, and we've talked about this, we've got our chair conformation. It's set up kind of like an Adirondack chair. Here's the back, here's the seat, and here's the legs. So it kind of goes down. And you could have the boat conformation, where this is, and it's already trying to twist on me, where you've got one end of the boat up and kind of the midsection and the other end. And it wants to twist either this way to have things push apart, or it wants to twist this way a little bit. So you have twist boat on those. And that works just with these models, even though there's no real interaction on these. And part of the reason for that boat is you've got these two hydrogen atoms right here trying to repel. And so if you can get them a little bit off center, that's a little bit better, a little lower energy. That energy table was shown here. The way most low energy, the least energy conformation is the two chair conformations, but you could go to half chair, boat, and twist boat. Twist boat is a little more stable than the boat I just showed you. What I didn't show you was the chair. it's kind of hard to do here. There's the chair. The whole thing is like a seat with one end sticking up. And if you go to make this with your hand, you can actually feel how that's hard to make and stabilize. Okay, going on to problem 27. Which I wanted to take a look at. There's this one. I don't know how y'all got the answers you did on this one. Still trying to figure that one out. All right, if you start with this, you have to keep in mind that this is a CH3, this is a CH3, this is a CH3. So if you are looking at axial hydrogens, and that's the way I read the question. Maybe I'm reading something wrong. This is page, hydrogen atoms that occupy axial positions. Well, there's one here, and one here, and one here. That's 3, 4, 5, 6, 7, and 8. That's what I get for axial. And then for equatorial, try to get something that's a different color here. So yeah, you don't count any of these. These are CH3s. So I got 8 axial. Unless I'm missing something, let me know in an email and I'll look at it. Then the equatorials, okay, you don't have one there, there, there. Here you've already got 1, 2, 3, 4 carbon. Here you've already got 1, 2, 3, well, on this carbon atom, you've already got 1, 2, 3, 4 bonds. Here you've already got 1, 2, 3, 4 bonds. So the only one, here you've already got 1, 2, 3, 4 bonds. So the only ones you can have equatorial on is this one, and it's opposite over here. It would be this one, but then this one. 2, 3, 4. Can't have one there. 5, 6, and 7. So I'm coming up with 7 equatorial. And none on this here or here or here because these are CH3s. Okay, so that's what I get. I don't know why you guys got what you got. All right, so let's go. Everything else looked good. This was the one I can't figure out how you got it. On 429, Maisie, you did the same thing I did, but I'm not sure that your reasoning was the same. But as I looked at this bromine back here, and I drew this guy, oops, a chair conformation for it. I wanted to put this one on the, okay, let me try this again. I decided not to go this route, where you go this way, and then draw a line there, and then one here, and then one here. I decided not to because that's kind of down and sticking up. And I guess you can put it here, but I decided to go the other way with it. I'm not even really sure now how or why I decided to go down the other way with it, but I did. And then you draw here, you draw here. So what I'm looking at with the molecule is this. If you look at it the way it's pictured there, then this is pretty much what you're seeing. Off the back, carbon. And this is the front one. And if we draw that as a chair, and I put it here, yeah, with this one down, no, with this one down. Okay, here we go. There's my chair. So this is what I'm seeing right here. High carbon, this one. High carbon, this one. Low carbon down here. And then it'll work the other way if you do it right. And then I rotated it this way and put it at the bottom of the chair. So I didn't change the conformation. I didn't fold or flip anything. I just rotated it. And so I rotated the whole thing around. Okay, so here's my V. Drawing this way, draw that line again, draw this line again, parallel, and then that one parallel to that one. Now I've got my bromine there, but when you do that, this one sticks up. Okay, now if I flip it, my chair this way, like was doing back here, if I flip from this chair to that one, or that one to this one, I think I'm going this one to the other one. Then, now I'm doing this. Starting with my V, drawing this way, that one again here, whoops, this one again here, and that one again here. Then I've moved my bromine up to here, where it's like that, where it's axial. So here it's equatorial, here it's axial. And so it would go from there to that, like so. All right? Now, for 4-30, I forgot to set this up. How much stuff I have? Okay, 4-30. Where'd it go? Probably gonna run out of time on this. But the gist of it is Maisie put this in an interesting way. Yes, it's hydrogen bonding. Okay, so if I take, let's see, I've got 1, 2, 3, 4, 5, 6, but I need an oxygen in here. When I forget what color my oxygen is, I want to say green. Oh, it's red. Okay, so if I do on this, take out here, and I put in a red. One, 2, 3, 4, 5. 2, 3, 4, 5. Okay, so there's one oxygen in there. And I want to change this one to an oxygen. Okay, and then maybe not have these correct, but and then one here. Oop, I didn't. I'm gonna take that out of there. I want this off of that. Okay, pretty much we got it. All right, so yeah, what's going to happen is this conformation here is going to want to be away from the other ones because, whoops, you're going to want it like this because there's hydrogen bonding between this oxygen and this hydrogen.